think we already talked about what I have on my first slide here. We did this, right? Pretty sure, yes, or what is it, Tuesday? What day is it? Thursday. Thursday, so we did Tuesday?
Yeah.
Okay. Yeah, we talked about the 3 types of motions you can have. Think of it this way. Think of vibrational motion going to be predominantly the only thing that a solid has. Okay, rotational motion is now liquids. Like, do liquids still have vibrational motion? Yes. Liquids still have vibrational motion, but liquids now are able to rotate. Like, you guys remember in physical science, right? The little solid particles just vibrating, and then liquids can do this. Right? You remember that? And then translational motion is specific to what? Right? Because they break away, they can go in straight lines. I suppose there's a little bit of translational motion in the liquid too, if you like roll it down a slide. I don't know. Alright? Alright, internal energy. So we're going to talk about really 3 main vocab words that we're going to spend most of our time talking about today are going to be temperature, thermal energy, and heat, and how they relate to each other. We're now going to introduce internal energy. Okay, because particles are so small, it's very, very difficult for us to measure the energy of one single particle. That makes sense, right? Particles are tiny. How are you going to be able to get the energy out of one single particle? You know, here's what internal energy is: the sum of the potential kinetic energies of an object's component particles. So it's specifically talking about how much kinetic and potential energy does one particle have. One little atom, one little molecule, one little compound, you name it, okay? Not easy to do. Okay, we're not going to spend really much more time talking about this because it's very difficult to do. All right, let's keep going. I don't know if do I have a definition of temperature in your notes?
Yeah.
I actually did put it in your notes?
Yeah.
Okay, good, because I don't think I have it, and I don't think I had it in your notes before. Okay, so what is the definition of temperature? Could you define it without looking at your notes? Do you remember it? The average kinetic energy in a system. So, can you explain what that means? The movement. Kinetic energy is movement. Okay, so essentially you're taking the average of your movement. So when you have a thermometer, what you're really doing is you're putting a thermometer in. Let's say you put a thermometer in something warm. Okay, well, energy gets transferred from the warm liquid or whatever you put the thermometer in to the liquid in your thermometer. But what happens as liquids get heated up, they get faster and they start to expand. And so what happens? It starts rising up the thermometer until it reaches its calibrated point that is whatever its temperature is. Okay, so the combined energy of a system's particles contribute to what we would call temperature. And I really want that so these are the 3 ones I really want you to get. I want you to know temperature. I want you to know thermal energy. We'll get to the other 2 here. And I want you to know heat and how they relate to each other. Because they have very similar ideas, but they're also very, very different. Okay? Now, you guys have all experienced this. You have, maybe just the ladies, but you got a cup of coffee. When you put coffee in your cup, originally the cup's pretty cool, right? It's room temperature. Okay, what happens over time? Okay, can you explain that process to me? Yes, the coffee's thermal energy is transferred to the cup. We haven't even talked about thermal energy. So what happens is the coffee's particles are moving really, really fast, right? Those particles in the coffee come into contact or collision with the cup. Okay? Energy from the coffee gets transferred to the cup during that collision. Does anybody know what that transferring thermal energy via contact is called?
Oh, it's convection?
No,
it's
conduction.
Yeah.
Convection is using different densities to usually liquids or fluids is how it would be like hot things rise, cold things fall, and you get this convection current that happens. That's what convection is. Okay?
I'm sure there's an explanation for this, but like when you pour hot water into like really hot water into a glass cup and drain it and put cold water in it, it'll break.
I'm sure it has to do with either expanding too quickly or compressing too quickly due to the changes in the energy. So fast. It just gives up, right? Trying to think of like an actual example, but yeah, like if you transfer energy too quick and the particles can't or don't have the pliability or malleability to react quick enough to this change in expansion or compression due to heat, it could break the particles. Not like the particles themselves, but the bonds between them. Yeah. Okay? All right. There's your definition of temperature. Okay, maybe what you do somewhere in your notes is you put these three definitions right next to each other so you can see how similar they are and how different they are. Okay, because they're very similar, but there is a subtle difference that's very important. Okay, is it very possible these three could be fill in the blank, short answer questions, and they all look very similar? Very possible. Okay? A little side note there. All right, there's our other one. Thermal energy. We've got some similar words in here. What are the similar words? Oh, they both have to do with movement. What's the different mathematical word, I guess? Average and sum. We understand average and sum, right? So if you were to take, from an average standpoint, you got this whole system, let's just say a beaker of water, all the particles, you take the average of how fast they're moving, because not every particle is moving at the same speed. If you remember, typically the faster particles migrate to the surface, and there's always some sort of evaporation that happens at the surface. Okay? Now, thermal energy is the sum of all the kinetic energies in a system. Now let me kind of explain a tangible example that I think you guys might be able to understand. Let's think of a bathtub full of water that is at, this might be too hot, but let's say 80 degrees Celsius. Yeah, you would probably burn yourself. But I'm just using it as an example. And then you had a cup of water at 80 degrees. Tell me are temperatures and thermal energies the same? Is there differences between the two? What are they? In what? Okay, so thermal energy is going to be higher in the bathtub because you have more particles. What about the average kinetic energy? The temperature, if they're both 80 degrees, their average kinetic energy is the same. That means you take an average of all of them, they're going to be the same. But the bathtub is going to have more particles, so therefore more thermal energy. So what would be more dangerous? Dump and pour a glass of water at that temperature, or plopping in a bathtub? And it has nothing to do with the temperature. It just so happens that the bathtub has a higher capacity or more thermal energy that it can transfer to your body. Does that make sense? Okay? Because it has more thermal energy, it can transfer more of it to your body than a cup of water. You can't really bathe in a cup, so I said pour in it, right? You could also say, well, the cup pouring on your head is only touching you for a short period of time. What was that, Tanner?
I said the cup size wasn't specified. You could just make a giant cup and bathe.
Yeah. You can always put my words on.
Tanner, do you have that page that you wrote?
Yeah.
Did you bring it?
He's always gonna say tomorrow.
Yeah, he's always got it, Gage. He just doesn't. He didn't bring it. Okay, we have a big day today, so let's stay on track. Okay, this should be should be pretty common sense, but I don't want to assume, okay, that energy only flows from higher temperatures to lower temperatures, never the other way around. Like your parents probably yelled to you, don't leave the door open, you know, it's hot outside, or don't leave the door open, it's cold outside. Does that mean like when it's cold outside, the cold air comes in? No, the hot air goes out, making the interior colder. Does that make sense? So it's not, the cold never transfers. It always goes from hot to cold, no matter what. Okay? However, for a refrigerator, you can actually put in work or energy to make it do the opposite, but that you actually have to put in work to do that. Right? That's how a refrigerator works. It takes out the hot. Okay? Alright, again, well, that's a whole other side topic. Alright, I'm not going to go elaborate any more on that. When does energy stop flowing? I don't know if maybe that's not a well-worded question. Yes, eventually it comes to a point where energy stops flowing between two objects. When will energy stop flowing?
Oh, and that
Equilibrium, in the context, equilibrium in this situation means equal what? Equal temperatures, right? So if I had, you know, a glass of water, I put like a really hot rock in this glass of water, what would happen? Energy from the rock would be converted to the water's temperature would go up, the rock's temperature would go down until they what? Okay, once they have equal temperatures, energy is not going to go back and forth. All right, heat transfer, there's my definition of heat. Okay? A transfer of thermal energy between two objects or substances is called heat transfer. So, temperature is the average kinetic energy. Thermal energy is the total sum of kinetic energy that you have in a system. Heat is when you take thermal energy and you transfer it from one object to another. So heat is a process. Does that make sense? Heat is a process. Heat only happens when you have different temperatures and thermal energy goes from one thing to another. Always hot to cold, right? All right, so how do you know heat is being transferred? What would be the obvious way to tell heat is being transferred? What if you can't tell it's getting hotter or it's getting colder?
It could be changing things.
That's a whole nother issue. that's energy going into the bonds versus causing a temperature change, in or out of the bonds. But here, listen very carefully. You know that heat is being transferred if there is a temperature change. But not always can you notice physically a temperature change, right? Would you be able to tell, like, even probably a 2-degree temperature change? Probably wouldn't even notice it. Hey, you know, when you walk into my room or out of my room, that's probably more than a 2-degree temperature change. Maybe you would notice a 2-degree temperature change. I don't know, but you wouldn't notice a 0.2-degree temperature change. Okay, so the way you know energy has been transferred via heat or thermal energy is going from one object to another is you would notice a temperature change. Do you see how all three are kind of related? Okay. Ooh, you guys should be pretty familiar with this, so I don't think I need to spend a lot of time. What does the word or the prefix exo mean? What does endo mean? And okay, so if I'm talking about exothermic and endothermic, it just is relating. What process are these trying to describe? So transfer via heat. So heat's the process. Okay? Exothermic would be thermal energy going out of your system. Endothermic would be thermal energy coming into your system. Example would be like, ever had those,
Turkey getting baked in an oven.
For Thanksgiving.
Yeah.
Right now. The mashed potatoes and stuff.
All right. You can always put food in the equation. How about something more simple, like, you ever had one of those like cold packs where you like smash and then over time what happens to it?
You're not supposed to do that.
The one where you break and it like starts getting colder.
Oh.
You know what I'm talking about?
Yeah.
You never seen those?
Yeah, I have.
I've seen them.
It's like portable. It's like a portable cold pack.
Yeah.
It has you break it and it has a chemical reaction inside. The chemical reaction is endothermic. So it takes energy from the bag essentially and the surrounding parts and it sucks it into itself, into the bonds. And so the bag gets colder. It's endothermic. Hot hands, have you ever heard of that? Like hand warmers? Do you know what hand warmers are?
Well, I'm assuming they warm your hands.
Little bags, like
hand
hand
warmers?
bags.
Like those bags with like those
Turn
little
your
beads
mind.
in them.
No, I'm
Nobody
not.
lives over 5 years without seeing.
I know what you guys are talking about, but
Okay, you know what I'm talking. You guys know what I'm talking about. The rest of you?
Yeah, the
Rest of
little
you know what I'm
bags,
talking
hand
about?
warmers.
You don't know?
It's so
It's just
weird.
the ladies don't know what hand warmers
No,
are.
I know.
It's even tiny little bags that comes in like new clothes.
They're like small little bags that have like these little like
Or else.
I don't know spherical materials inside, and you like bend beads. You like bend them, and then there's a chemical reaction. Hey, yeah.
Yes, we use them when my sister has softball. It's so
Typically, yeah, in sports we'll use them a lot. Like if it's in the cold, like football when it's cold, they'll put the hand warmers like in their pockets or in their
Oh, I have a few at
pouch.
home I can bring some.
You have some at home? You're not very good at bringing stuff in when you ask me.
Those bags will
Oh, but
bathroom.
Alright, so the point here is this exothermic hot hands, what happens is there's a chemical reaction where it gives off energy. Okay? And technically your hands are the surroundings. So what happens? Your hands get warm if you're touching it. Okay? I know it's kind of hard to realize that like energy going in makes everything surrounding it cold. Energy going out makes everything surrounding it warm. Okay? Because the system is usually a chemical reaction. Okay? Like bonds of a particular type. Ooh, Kelvin scale. Yes, you should be familiar with this, but let's review the 3 types of. You don't remember the Kelvin scale? You guys.
No, it's
You said
273.17 point something 5. 273.
6'5".
1.5. Wow.
Look in your
Okay, I
imagination.
really wish I would have paid
They were trying to do it without
Oh, yeah,
looking at
it's right there,
it. What are the 3 temperature
Oh, it's
scales?
right there.
Thank you.
Celsius, Fahrenheit, and Kelvin.
All right. Okay, which one's the dumbest?
Fahrenheit.
Fahrenheit's the one Americans use. And just, I mean, what is the boiling? Do you even know what the boiling point in water is on the Fahrenheit scale?
212.
Yeah.
All right. I'm actually surprised you know that.
I didn't.
Because we learned it last year.
Oh.
Yeah.
If you didn't learn it last year, I mean, it's such a weird random number, man.
Well, 273.15 isn't random?
Oh yes, but
Yeah.
there's a different purpose for the Kelvin.
But isn't-
scale.
isn't,
That goes beyond simplicity from a number.
Isn't the boiling point for Celsius?
100, yeah.
And it's 0.
0 degrees is the freezing point of water in Celsius. 100 degrees is the boiling point of water in Celsius.
But-
What is it? Negative 32.
No, it's actually just
It's
32.
32.
I'm so used to the Celsius scale. I don't even know what the Fahrenheit is.
But we should
No.
use the Celsius scale. It's so easy. You divide by tens.
There is a.
It's
That is actually
based.
not easy.
It's not easy because we're not used to it. But it's based on the metric scale. It's the same purpose of the metric scale.
Wait, there's no absolute 0 Kelvin?
What do you mean?
There's
you
no
don't have-
negative Kelvin.
Yeah, absolute 0 is 0.
Yeah, absolute 0.
It's not possible. Yeah, we'll get to that today.
But, yeah,
Okay.
I'm not saying it.
Consist of all positive numbers. Okay, well, the main reason why we use the Kelvin scale, Tanner, are you paying attention? I know the answer to that, so I don't know why I asked. The main reason why we use the Kelvin scale is this. It doesn't have any negative numbers. So the coldest you could possibly ever get would be what?
Absolute
0.
0.
So 0 and has 0 degrees Kelvin, and over time, it's a nice linear line. That works out really nice when we start using temperature in various mathematical calculations in chemistry, because it's linear. Linear math is real easy, isn't it? At least much easier than doing a parabola or doing an exponential graph or a logarithmic graph, right? Would you all agree with that?
Yeah.
Okay, much easier. Okay, when you've got the negatives, what it ends up doing on the Celsius scale is it makes that line no longer linear and it makes it much more difficult of a math problem. And we like simple, right?
Yes.
So we're going to stick with the Kelvin scale.
Okay.
Cool?
I like it.
Absolute zero. This is your theoretical coldest you could ever get, which we've never actually got. So what that simply means is it's the coldest you could ever get something that it would still be moving ever so slightly, because if you get any colder, at actual absolute zero, is when all things cease to move. And people will theorize that because it's when objects stop moving, they don't exist, and so they say that it's just not possible. I mean, could you ever reach if everything goes from hot to cold, could you ever reach the coldest thing?
No.
Because you couldn't get any colder.
Unless you're in a total vacuum.
Yeah. You could never reach the coldest thing if that's how that works. So
Yeah.
I think that's cool. Now this would be technically what it would be in Celsius. I know that seems like a goofy number. We're actually probably just going to take the 0.15 off to make it easier.
Why is it so specific for like absolute zero?
Yeah, so they've gotten whatever 0.000000. I don't know what the actual number is that they got, but
Is there an absolute too hot?
well, I don't know if we would ever have an equipment enough to be able to handle that.
Maybe the sun.
It's like could we hold the sun in our?
But the sun's not even the hottest one up there.
No, it's not.
I heard
That's true.
there's some planets that their core is so dense that a tablespoon of it would be like some million tons.
Yeah.
Uh-huh.
That's
That's
not
awesome.
absolute zero, but
You can just see like
it's
like a
absolute.
Alright, so this is our third law of thermodynamics. This is the absolute zero law. So what's the first law of thermodynamics? Quick review.
Matter and energy. Only changing forms.
Okay, somebody else, not these two ladies. Tell me what the second law is.
Wow.
Things progress from order to disorder.
Yep.
Or something.
Yep. Law of entropy. Entropy is a measure of disorder. We know that everything goes in a more disordered fashion naturally. Okay, if you put dissolved salt in water, the salt particles in the water don't migrate all to the bottom left corner and just sit there. It's a probability thing. Okay, and believe it or not, dissolving salt is actually an endothermic process, which means it requires energy to do it. But because it makes the positional probability greater, aka it makes it more disordered, it dissolves pretty easily. So really, it's a twofold thing. It's energy and it's disorder that makes something likely to happen. And we'll talk about that much later in chapters 13, 14, and 15.
Would it eventually get there? You said let it sit there for like a year, just didn't touch it.
Yeah, it would. You don't need to stir salt to get dissolved, even though it requires energy, because of the fact that the whole second law idea that it wants to be more disordered, it will essentially just disorder itself. Now there could be some sort of thing that it creates some layer that, kind of similar to like you do if you're in an ice bath. And, I guess I don't know for sure. Oh, so third law. It's the physical law saying it's impossible to reach stopping movement, if you will. Okay, but we said the coldest you could ever get would be when particles stop moving, because movement is very much part of temperature, right?
Very much so.
What's temperature?
Average.
The average
Energy.
measure of kinetic energy.
Okay, what's thermal energy?
No, it wasn't.
Salt.
Would you have any carbon motion when your dad smells?
Yes, because
Vibration.
You'd be deteriorating over time, and
I love it when that happens.
Technically, dead people are always here
snap.
because their body decays into what? The soil. So basically, you destroy quite a bit of dead people.
What's this
Yup.
show on Netflix called White Collar?
White collar.
Oh, my dad's watching that.
Yeah,
right
it's
now.
so good. Anyway, this guy has like this insane comic collection, and he stole some of it, so these detectives were going in to get it back, and they get into the thing,
and then once they touch one comic book, it closes down and it starts a vacuum, and they can't talk to each other and they can't breathe. So they're like trying to get out and they can't talk to each other and they can't breathe. It's so crazy.
Wait, this person that has his comic books created a vacuum so that if you got in there you would die?
It was for, oh no wait, what happened is the fire alarm would trigger that, so his comic books would not catch on fire. So they pulled the fire thing on purpose so it would lock in on them, I think, to stall for time. They had these little breathalyzer things, but then they ran out, so they were like panicking and they couldn't talk to each other because it was a vacuum.
You guys know why you can't talk to each other in a vacuum, correct?
Sound energy.
Yeah, there's no particles for sound to vibrate through.
So, it just goes like.
Wait, so what?
Alright, there is a couple of math problems here, but they're so easy that I don't think I really need to go over them. But here's your equation. In fact, you can get rid of the 0.15. We'll just make it easy. I like whole numbers. Cool? So what we're going to do is, this would be temperature in Kelvin, so if you want to put a K there, you can. But here's how you would convert from Celsius to Kelvin. You add or subtract. Wow, that's hard. Can we do that?
Yes, we can.
So if we look at this, what is the temperature in Kelvin? It gives us Celsius. Would we add or subtract that?
We would add it.
Yes, 273 plus the 32.5 would give us our Kelvin temperature.
305.
Yes, we believe.